Keeper 2.5, limits involving infinity. Okay, before we actually start looking at limits to infinity, we want to do a quick review on vertical and horizontal asymptotes. I know you've seen them before in Algebra 1, Algebra 2, probably even a little bit in pre-calc, but in this class we want to be sure that we're denoting or we're justifying our asymptotes using limit statements. So for a vertical asymptote, we say that we have one or one exists if the limit as x approaches that number, wherever the asymptote is, goes off to infinity or negative infinity. So again, the limit as x approaches the number goes to infinity or negative infinity from the left and from the right hand side. For horizontal asymptotes, we're talking about, our end behavior. So we say that the limit as x approaches either positive or negative infinity equals some number. I just called it b. All right, so again, for horizontal asymptote, we're looking at what it's doing off to infinity. We want to make sure it's approaching an actual number. All right, so how do we find our asymptotes? Again, this is just a quick review. For vertical asymptotes, first you want to factor your numerator and your denominator. The reason you want to do that is to make sure that you don't have any holes or removable discontinuity in your equation. If you do have a hole, you want to go ahead and take that out. And then step 2, you want to set your denominator equal to 0 and then solve for x. And you always write your answer for vertical asymptotes in the form of x equals some number. For horizontal asymptotes, we have 3 different cases. So case 1, if the degree of the numerator is equal to the degree of the denominator, then your horizontal asymptote will be y equals the lead coefficient of the top over the lead coefficient of the bottom. For case 2, if the degree of the numerator is less than the degree of the denominator, your horizontal asymptote is y equals 0. For case 3, if your degree of your numerator is greater than the degree of your denominator, you have no horizontal asymptote because it goes off to infinity. Don't forget, you can have what we call a slant asymptote if the degree of the numerator is 1 more than the degree of the denominator. All right. Okay, let's start with a very easy example, 3 over x minus 2. The first thing I do is I look to check to make sure that this function can't be factored. This one is in its simplest form, so I can just go ahead and start working with it. If I want to find the vertical asymptote, I take my denominator and set it equal to 0. So I take x minus 2 equals 0, and I solve it, and I get x equals 2. All right, so now I'm going to come over to my graph, and I'm actually going to graph that out. So I have a vertical asymptote at x equals 2. All right, now I also have a horizontal asymptote, and I know where the horizontal asymptote is because I can look at the degrees of my function. So the degree of the top is 0, and the degree of the bottom is 1. So the degree of the numerator is less than the degree of the denominator. That tells me that I have a horizontal asymptote at y equals 0. And so again, I'm going to graph that out. All right, so now I'm going to draw out my curve. Again, you should kind of have an idea of what this looks like based off the parent graph. But if you didn't, you could always find your x and y intercepts. Now this one isn't going to have an x-intercept because of the horizontal asymptote at 0, but I can find the y-intercept, and the y-intercept would be when I plug in 0 for x. So if I put 0 in right here, I would get 3 over negative 2 or negative 1.5. I know it's crossing somewhere down here. And if I curve that out, and I make my top piece just off the basic form of a rational, that's the graph that I'm going to get. Now, how do I know for sure that this is the vertical asymptote? Well, when I look at x equals 2, I see on the right-hand side it's going to infinity, and on the left-hand side it's going to negative infinity. Well, that's the definition of an asymptote. So my justification, I would simply say, the limit as x approaches 2 from the right, f of x equals 0, and the limit as x approaches 2 from the left, f of x equals negative infinity. If I do the same thing for my horizontal asymptote, I can see my wings or my end behavior, both pieces are going to 0. So as x goes to plus or minus infinity of f of x, our limit would be 0. All right, let's look at another example where we're graphing the function and we're determining our asymptotes. the very first thing that I would do is I would factor out my function to see if I have anything crazy going on, anything like holes or just anything weird that could be happening with the function. So again, the first thing I'm going to do is factor it. I factor out my denominator. I get x plus 3, x minus 2. Immediately, I notice that the factor in the numerator of x plus 3 is the same as the factor in the denominator of x plus 3. And anytime you have a factor that's the same, that's going to give you a hole or removable discontinuity in your graph. So I'll cancel that out, and I'll just take note that that is a removable discontinuity. Once I remove that factor, I want to rewrite the equation in the simplest form. So I get 1 over x minus 2. Now, to find my vertical asymptote, I'm simply going to take my denominator of x minus 2, set it equal to 0, and solve. So when I solve it, add 2 to both sides, I get x equals 2. For horizontal asymptote, I'm going to look at my 3 cases or my 3 rules. And if you notice, the degree of the denominator is greater than the degree of the numerator. Therefore, we have a horizontal asymptote at y equals 0. So from there, I'm going to go ahead and put my asymptotes on my graph. So I'm going to start with x equals 2. And then I'm going to draw in my y equals 0 for my horizontal. I also like to go ahead and try to find a y-intercept. So to find my y-intercept, I'm going to put 0 in for x. So if I put 0 into my simplified equation for x, I would get a y-intercept of negative 1/2. And I'll plot that on my graph. I also like to, since I had a hole in my graph, I also like to plot the hole. And if you remember, your hole was at negative 3. So if you take your negative 3, plug it back into the simplified function, you get 1 over negative 3 minus 2, or 1 over negative 5, or negative 1/5. So negative 3, negative 1/5 would be my hole. And I'm just going to go ahead and put a hole there on my graph at approximately negative 1/5. I like to do my hole in my y-intercept first because it tells me where my curve is going to go. So I know on the left-hand side of my vertical asymptote, the curve is going to be below the graph. And on the right-hand side of my asymptote, because the original curve is below, the next curve is going to be above, following like my parent function, my parent graph. So that's what my graph looks like. Now to justify my asymptotes, the first asymptote we said was x equals 2 for vertical. In order for this to be an asymptote, by definition, as my graph approaches 2 from the right or the left, it has to go to infinity or negative infinity. From the graph, I can see that as x approaches 2 from the right, my graph is going up to infinity, and as x approaches 2 from the left, my graph is going to negative infinity. So I'm just going to simply state that in limit form for my justification. Again, you need to write it in limit form. You can't just write it in words. You actually have to write the limit statement to justify your actual asymptote. For the horizontal asymptote, again, I'm going to do a very similar thing. I need to look at my right-hand side of my graph, far right and far left, to see if it's approaching some number. If you notice, as x goes to infinity, the graph is approaching 0. And as x goes to negative infinity, the graph is approaching 0. Therefore, my justification would be the limit as x approaches plus or minus infinity of f of x equals 0. All right, so the first couple examples, we did it with a graph. You don't need to use a graph to do it. You should be able to just look at the function to figure out the actual limit. All right, now when they're asking for the limit to infinity or to negative infinity, you're considering your horizontal asymptote. That's what you're looking at. You're looking for your horizontal asymptote. So in this very first one, I want to find my degrees. So the degree of the top is 2, and the degree of the bottom is 1. Since the degree of the top is bigger than the degree of the bottom, my limit is going to equal infinity. It follows whatever this is. All right, the next one, I have a degree on the top of 1, and I have a degree on the bottom of 2. The degree of the top is smaller than the degree of the bottom, so my limit is going to equal 0. Okay, let's look at 2 more examples. So in this first example, in number 3, the very first thing I'm going to do is I'm going to distribute or FOIL out my denominator. So when I FOIL out my denominator, I get negative 2x squared plus 5x minus 3. Okay, now I look at the degrees. So the degree of my numerator is 2. The degree of my denominator is 2. Since those degrees are the same, I know that I'm using my rule for horizontal asymptotes, and my limit should be the lead coefficients. Well, the lead coefficient is 6 over -2, which equals -3. All right, the next example is a little bit more challenging. What I like to do is rewrite it as a behaves like. So when I rewrite this function, I have to say behaves like because I'm not writing the actual function. I'm not writing what it actually originally was. I'm writing what it's acting like. So for me, what I'm going to do is, because I'm only concerned about the highest degree, I'm going to say this thing behaves like the square root of x squared over x. In other words, I'm ignoring the 1. So I'm ignoring this 1 in the beginning, and I'm also ignoring the 4 in my denominator. All right, so if it's behaving like that, my next step would be to go ahead and take the square root of the top. Well, the square root of 4x squared is 2 absolute value of x. Since our limit is going to negative infinity, the absolute value of x would actually be negative x. So if you remember from the prerequisite unit, when you have absolute value, it can be positive or negative. And again, since it's going to negative infinity, our x is going to be negative x. So then I would end up with the limit as x approaches negative infinity of negative 2x over x. The degree of the top is the same as the degree of the bottom, so that means my limit would be -2. All right, the next one, the next couple, I want to think about it graphically. I want to kind of picture the graph in my head. So the limit as x approaches infinity of cosine. Well, if you remember, cosine is just like a wave, and it's going back and forth between -1 and 1 all the way out to infinity. So this limit would actually not exist because it's oscillating at an even height. It's never reducing, it's not decreasing. The next one is a linear equation with a negative slope. So it's doing something like this. And so the limit as I go to negative infinity, or as I go far left, so if I go this way, is going up to infinity. Number 7, we have a quadratic equation, and it's negative, so it's upside down. So it's doing something like that. And the limit as x approaches infinity, either infinity or negative infinity, doesn't matter. Since it's upside down, both arms are pointing down, I get negative infinity. Number 8 is pretty much the same thing. We have the limit as x approaches negative infinity of 3 minus x squared. That's the upside down parabola. So even if I'm going to negative infinity, it's still facing down, so this equals negative infinity. The next one, we have e to the absolute value of x. If you remember from your prerequisite work, this graph pretty much, well, your e graph, I'll start with e. E looks like this, but if we want the absolute value of x, our left-hand side is going to equal our right-hand side, so it's going to look something like that. And so as I go off to infinity, I get infinity. It's going up. Similarly here, if I think about the graph of this, it's like that. As I go off to infinity, as I go far right, this equals infinity. This one, we have ln negative x. And so that negative x is simply reflecting it over the y-axis. So here's the regular ln graph. And here is our ln negative x. And so as we go far left to negative infinity, our graph is going up to infinity. And then number 12, this graph, negative ln x, that is going to reflect it over the x-axis. So instead of something like this, we're going to end up with something like this. And so as I go to negative infinity, well, I never go to negative infinity because I have asymptote at 0, so this does not exist. All right, the very last thing I want to talk to you guys about today is the squeeze theorem. The squeeze theorem is basically a theorem that we use when we don't know what the graph looks like and we can't figure it out, but we do know what graphs between that graph looks like. So basically the idea behind this theorem says if you have some function, let's say a function that looks like that. Let's call that function h. And let's say we're at some point A. And we're trying to find the limit as x approaches A of that function. So we want to know like what this limit value is from the left and the right. But we don't know. We can't figure it out. We don't know what the graph looks like. We can't do anything. But let's suppose that we had another function. Let's call it g. And we had another function, maybe something like that. Well, let's call that f. If we have two functions g and f that are between h, and f equals g at this point A, so they're actually touching each other at that point, and h is in between them, if we know the limit of f and g, we could also find the limit of h. So again, if the limit of f equals the limit of g equals some number, like it's the same number, and h is in between, so h is between f and g, then h will have the same limit as f and g. All right, so let's look at an example of that. All right, so here we have the limit as x approaches infinity of sine x over x. You guys probably don't know what that function looks like. You probably didn't do any graphs like that in pre-calc. But again, if you can use some other knowledge to figure out functions that you do know, then you can figure out your answer. So the first thing I'm going to start with is a known fact. I know that sine is between -1 and 1. And I also know that if I divide everything by x, I'll get this sine x over x. So -1 over x is less than sine x over x is less than equal to 1 over x. All right. If I can figure out the limit of the -1 over x, and if I can figure out the limit of the 1 over x, and if they're the same limit, then that's going to be the answer for the limit I'm looking for. So let's see. The limit as x approaches infinity of -1 over x. Well, again, that's just a rational function flipped over the x-axis. So this is going to actually be zero, excuse me. Because we have a horizontal asymptote at 0. And then we have the limit as x approaches infinity of 1 over x. And again, because we have that horizontal asymptote at 0, our limit is 0. Well, since our two functions equal and sine is between those two functions, the limit as x approaches infinity of sine x over x is equal to 0.